Welcome back. This is Professor Nading, and we are going to work on section 6.3, the distribution of a difference in proportions. So if you remember last time, we ended with 6.1, not 6.2, where we worked on a single proportion. And in that, we discovered that if we could find that a group had a substantially large n value, in other words, the CLT or the central limit theorem, if the proportion multiplied by the group value was greater than or equal to 10 for both groups, then we could utilize the distribution of a proportion and trust that its curve would be normally distributed. Well, today we're going to look at two groups in comparison to one group. And we'll also calculate the standard error slightly differently when we get there. So you'll need to have your formula sheet ready for this. So let's analyze. Slide says we are not, underlines not, dealing with two different proportions computed from the same group. Keyword here is same group. Matter of fact, I'm going to get myself a highlighter here so I can do a little highlight work. And I think I'll grab a highlighter and from the same group right there. Pretty sloppy, right? Sorry. So first one, proportion of students who are math majors and the proportion of students who are economic majors. These are not crossover groups. These are the same group. Excuse me, these are not from the same group. They are from a completely different entity, if you will. So when we talk about a proportion from or two proportions of the same group, we're looking for instance, both male and female in a math major, male and female in an economic major. We have to differentiate between two separated groups or two groups within inside the same group. An example which is not proportion of math majors who are women, proportion of math majors who are men. Again, we're not inside of the same group. The group is women. Okay, the group is men. Now, if we're talking about the group is math majors, now we can have proportions of men and women inside of the math majors. Identify two groups within a sample and compare the proportions between the groups. Okay, correct. The proportion of women who are a math major and the proportion of men who are a math major. Note the notation of the women or the gender comes far before anything about the major. Where up here, we had the major listed first, and then we discussed with inside. So we want to identify our groups prior to looking at the single group they come from. Oops, sorry, back up. The proportion of math majors who are women and the proportion of economic majors who are women. So now we have groups of different economic majors, but all within inside the major group, if you will, of women. Here's a nice one to take a look at. And in this particular situation, we're supposed to look at and compare, do we have one group or do we have two groups? And does the method apply for the difference of proportions? In order for the method of difference of proportions to apply, we have to isolate and find two separate groups. And I'm going to switch over here to a pen. Get myself some kind of color I prefer here. Okay, so let's take a look at the first one here. So it says compare the proportion of students who use Windows-based PCs to the proportion who use a Mac. Okay, well that's a no. That's a one group. We have these students using the Windows. That's a group of people which are completely separate from those who use a Mac. That's a different group. And the answer is no. We're not inside the people who own this PC and asking something about them. In letter B, compare the proportion of students who study abroad between those attending public universities and those in a private university. Okay, well, now we have two groups. Now we have those who are studying abroad as a larger group, and within inside of that, those who are a public and those who are attending a private university. Yes, we have two groups here. And yes, we would be able to apply the difference of proportions. Compare the proportion of in-state students at a university to the proportion from outside of the state. Okay, now in this one we have at a university. Okay. So it's a single university, and all we've done is split from the two. So the answer is going to be no. Second one, compare the proportion of in-state students who get financial aid to the proportion of out-of-state students who get financial aid. Definitely two different groups there. We have two groups going on. And with inside of there, we can calculate two groups. Jump down to the next one. In a taste test, compare the proportion of tasters who preferred one brand of cola to the proportion who prefer the other brand. Okay, and it's the proportion of tasters in a taste test, the proportion of tasters who prefer one brand of cola to the proportion who prefer the other brand of cola. Again, in this particular value, we're not doing two separate groups. We have a single group of people who are just yes and no on the Pepsi or the Coke or whatever it happens to be. We've done this test before with a single proportion. We've tested to see those who prefer Pepsi compared to those who don't prefer Pepsi. Compare the males who voted in the last election to the proportion of females who voted in the last election. Now we have a group of two. Two separate groups, proportional values being compared to each other. Up here, a group of people being split into two different groups. Not the same thing. Letter C. Compare the graduation rate of students on an athletic scholarship to the graduation rate of students who are not on an athletic scholarship. Well, there you go. So yes, we have two groups. We didn't go to everybody on a scholarship and split them into two groups. We went to all of those proportions of students who were on an athletic, so that was a group, and that could have been 700 people. And then we went to another group of people who were not on an athletic scholarship, and that could have been 800 people. And those are just arbitrary numbers, obviously. Whereas, and I'll go back up here to this one, that was a no. This was the taster. So this was just a group of, let's say, 1,000 people. And then we broke them into two separate items. Where down here in letter C, we have two completely different segmented groups of people. And the last one, compare the proportion of voters who voted in favor of school budget to the proportion voted against the budget. Again, that's a single group of people split into two groups. And the answer is no, because that's a single group. The key in these is finding, are we taking a single group and splitting it into two, or are we actually comparing two different groups of people? So let's take a look at the central layering theorem for two different groups. And you can see the notation change of p hat 1 minus p hat 2. It says n is sufficiently large. Remember last time we checked n sufficiently large if it was greater than or equal to 10. We'll do exactly the same thing with these values. And the formula gets much more complicated looking, but it's really not an issue for you, I don't think. First of all, here's what it's telling you. It's telling you that the stat that you are talking about, right, the statistic, the best point statistic, p hat 1 minus p hat 2, so we're actually going to take two numbers and subtract them and have a stat here, will be normally distributed. That's what this means here, normally distributed. Around the curve, this will be our center. Remember, this is our center population parameter, comma, and this will be our standard, this will be our measurement of error. Our measurement of error is pretty large looking, but it's really not going to be an issue for us. Now, one of the things we want to understand is that these values here, these p, stand for our population parameter. Right here. These p values stand for our population parameter. However, we don't know the population parameters, so we are going to change these out with p hats like we did in the last formula. It says a normal distribution is a good approximation as long as, and here we go again, as long as when we take the first set, multiplied by the proportion of, so the n value times the proportion has to be greater than 10, and then we have to do the counterpart. But then we also have to do the same thing with the second set, and it has to be greater than 10, as well as its counterpart. So it's actually going to take us 4 calculations if we have to do it manually. But it does give a nice note here. It says in practice, you can just make sure that the count in every cell of the two-way table is at least 10. And generally, that's what takes place. Not always, but if we have a two-way table, as long as all the numbers inside are bigger than 10, then we're okay. If not, then we'll have to do the calculation. So first question, here we go. Consider random sample size of 86 from a population A with a proportion of 0.1 and random samples of size 64 with a population B of proportion 0.10. Find the standard error of the distribution of the difference of sample proportions for p hat A minus p hat B. Round your answer for the standard error to 3 decimals. Okay, so here we go. So, and also it goes on to ask us, is this large enough for the central limit theorem to apply? Okay, so I'm going to escape out of here and discard. I'm going to bring up this here. Let me do a little bit of writing here. All right, now, so let's start here. So first of all, what do we know? Well, what we know is, and let me grab it real fast. What we know is that according to this, that we have sample size. There we go. It was a little large. I can't really see it. I'm sorry. Give me 1 second. There we go. We have a sample size of 86. So we have a sample size of 86 with a population proportion on A at 0.41. And we have an N value, which is equal to 86. For population B, and remember these are p hat values, that we have a 0 or a 10%, 0.10, and we had an N value of 64. So the first thing it asked us for was the standard error. Okay, well, remember that the standard error is a calculation that uses our root of p hat 1 times 1 minus p hat 1 divided by n of 1 plus p hat 2 times 1 minus p hat 2 divided by n2. And if you're looking to see where I'm getting that at, I'm pulling that right from our formula right here. Remember, the z, when the z gets multiplied against this value, just like we did in the single proportion, remember, this is the standard error, and combine these two things are the measurement of error. Right now, they just want the standard error, but I'm in the difference of proportion, so I have to use this formula for the standard of error. When I multiply it by the z value for the proportion, I'll get the measurement of error, and then when I take p1 minus p2, I'll actually get the statistic, or where we're centering up at. So let's plug some numbers in. So we have root of 0.41 times 1 minus 0.41. N size for this one was 86. Plus the second one was 0.10 times 1 minus 0.10. And the second set was 64. Take your calculator, plug all that in, and 0.065. That's my standard error. So the second question in the book, or in the slide, so 0.065 right here. And the second says, are the sample sizes large enough for the central limit theorem? Okay, well, we're going to have to calculate those. So let's go do those off to the side. So in our first one, we have to take a calculation. Remember, it's this value multiplied by this value here. So in my first calculation, it's 0.41 multiplied against 86. Which is 35.26. That one's good. Now remember, though, that this 0.41, its counterpart also has to be multiplied against 86. Well, if 41% was greater for 86, then 1 minus 0.41 is also going to be greater because it's a greater percent, if you will. And I'll just do the calculation for you. 1 minus 0.41, that's 0.59 times 86. It's going to be even bigger. It's 50.79. 74, sorry. When in practice, what I really do, I go to this one over here and I always grab the smaller value. And then I check my smaller value and I see if my smaller value actually makes it. So far I've got this one and I've got this one. I'm now going to check the 10% value because I can see right away that 10% of 64 is only going to equal 6.4, which is not going to work. But if I took the counterpart of that, 0.9 times 64, I'd actually get 57.6, which is okay. But remember, one thing that doesn't make it tells me no. So when I go back to the formula, I'm going to have to say no right here. We'll go to the next one. So we had two answers, 0.065 and no for the central limit theorem. Confidence interval for p hat 1 minus p hat 2. We use our statistic and we add and subtract z times the standard error. We've done this over and over again. But remember now, our statistic is p hat 1 minus p hat 2. We'll substitute all p values out for p hat because that's the best guess that we have. We don't know p. And we'll use our z star from the confidence interval that we're given. And remember, we can go back to our formula sheet to get a different z star value, at least for 90, 95, and 99. If we need to calculate anything different than that, then we can use our calculator to get that z star value on a standard normal curve. So everything's the same here as what we just did. The only additional thing we're doing to the last question is we're going to multiply by z star, and we're going to add and subtract that from the statistic that we have, which is p hat 1 minus p hat 2. So let's go do that. Errors in medical prescriptions occur, and a study examined whether electronically prescribes may help reduce errors. Two groups of doctors used written prescriptions and had similar error rates before the study. One group switched to e-prescriptions while the other continued to use written prescriptions, and the error rates were measured 1 year later. The results are given in Table 1. One is to find a 99% confidence interval for the difference in two proportions. So they want us to use PW written minus PE electronic, where PW is the proportion of errors using written and PV is the proportion using e-prescriptions. Round your answers to 3 decimal places. So we need a 99% confidence interval level, which means we're going to have to utilize our formula, and we're going to have to come up with a number of different things here. First of all, if it asks us, and I don't see, if it asks us, completely took off there, didn't I? If it asks us if the central limit there to apply here is an absolutely yes, because look at the box that no number is less than 10. And we don't have to do any calculations at all because we know that we have 254 as our smallest number, and that's far greater than 10. So let's get our numbers and let's do some calculating here. So let me switch over so we can do some writing. Okay. All right. All right. So where are we here? What do we know? So first of all, we know that the proportion of written is 1,478 out of 3,848. And if you get that into a decimal, that's 0.384. So there's my first W, or my first p hat value for written. I'm going to do my p hat value for electronic. These are 254 out of 3848, same number. And that's 0.066. Okay. We're on a 99% confidence interval level. So if I go to a 99% confidence interval level and I look for my Z star, 2.576. Z star is 2.576. We definitely need that. All right. Now remember, here's what we're doing. We're taking the stat. We're going to add and subtract z star. And then we're going to multiply it times the standard error. Now, it's going to be awfully large, though, but this is how simple it actually is. So first of all, where does our stat come from? Our stat comes from PW minus P hat E. That's where our stat comes from. We know that our z star is 2.576 because we already calculated that. It's going to get multiplied by our standard error. And remember the standard error of our formula. I'm working in right here, confidence interval, difference of two proportions. I'm following this formula right here. This is going to be my standard error right here. So I'm going to take p hat 1, which is 0.384. I'm going to multiply that by 1 minus 0.384. I'm going to divide that by the value of n, and both n's are the same. And then I'm going to add that to exactly the same thing, but for the second set, which is 0.06. 6. 1 minus 0.066. And this is also divided by 3848. Give you a second and let you go make that calculation and see what you come up with. Okay, so if I take these two, if I take p hat w minus p hat e right here, 0.318 plus and minus 2.576 times, because that's what this means when this is up against here, times, if I roughed this out, just so I can show some numbers here, 0.0088. That's really my confidence interval level so far. So let's do the first one. Let's take 0.388. Let's subtract 2.576 minus this value, and let's get 0.295. There's the bottom end of my CI. Now let's do exactly the same thing, but this time let's add 2.576 times this value, and let's get 0.341. Okay, I like that. I'll scoot that over just a little bit right there. Now, I want to scoot back, and I want to go back to where we are, answer the questions that we're at. So first of all, the question is, what's the 99% confidence interval level? We just did that. We just got 0.295. Oops, back it up. It's got 0.295. I'm trying to write on here. There we go. And we just got 0.341. Perfect. Is it plausible that there is, and here's the key word right here, no difference? Well, what's no difference mean? No difference means that if I took p hat of w and I subtracted p hat of e, no difference means I would see a 0. Okay, well, look at your confidence interval level. It goes from 0.295 to 0.341. 2 chapters ago, we talked about if this value is not inside of the CI, then it's not a plausible solution for this. So our condition or our statement is no. 0 is not inside of here, and we would not utilize that value. Hypothesis testing. So on a hypothesis test, we are going to now look for z value instead, okay? The standard error is still the same, but the difference is that the null hypothesis is true. We'll change h of o out to say that p1 equals p2. Remember also, that also means that p1 minus p2 equals 0. The null hypothesis is centered up at 0. We will be using what's referred to as a pooled proportion in this problem. If you look down, it says pooled proportions. We assume that the proportions are the same between the two groups, and we want to use one proportion that is our best guess for what that would be. Combine both groups into one big group and use the overall proportion called the pooled proportion. And notice that it looks very similar. They use a statistic that has a p-hat value inside of it right here. And that p-hat value looks very super similar to what we've already been using, but the p-value is slightly different. I'm usually going to write the word pooled just to simply be clear with you and make sure where we are. And the place we'll notice that pooled proportion takes place when we're doing our z statistic. It's underneath of our root. Okay, so let's try one. And again, this is for hypothesis testing. Now here's the calculation. In order to calculate z, the standard has always been take the statistic, subtract the null, and divide by the standard error. Okay, well, our statistic is p hat 1 minus p hat 2. Our null is minus 0. Matter of fact, when we go to our formula sheet, you're going to notice that there's an insertion, just to make everything clear, of a minus 0 right here in your formula. Divided by the root of, now it's important to realize that these values here are our pooled values, okay? This, and this are all from our pooled p-hat. Okay, so we'll calculate a pooled p-hat. It says if n times p-hat is greater than 10 and n times 1 minus p-hat is greater than 10 for both samples, then the p-value can be computed as the area of the tails of a normal distribution beyond z. And that's really what we're trying to get at here, is we're trying to calculate the value of the p and whether we can reject the null hypothesis or not. So, question, here we go. So using data from the study, we find a significant difference in the proportion of fruit flies surviving after 13 days between those eating organic potatoes and those eating conventional potatoes, so P of O and P of C. This exercise asks you to conduct a hypothesis test and use additional data. H of O is P sub O equal P sub C. If nothing's going on, then the organic is exactly equal to the conventional. However, though, if something is going on, then the organic measurement will be greater than the conventional method. It says where P of O and P sub C represent the proportion of fruit flies alive at the end of the given time frame of those eating organic and those eating conventional. We have N value and N value 2 both at 500. So both of the N's are 500. We're testing at a 5% significance level, and we're looking at the effect of the organic raisin after 20 days. Okay. So here comes our stats. After 20 days, 275 of 500 fruit flies eating organic raisins are still alive, while only 170 of 500 eating organic are still alive, or eating conventional, are still alive. Give the test statistic and the p-value. Okay, so we need a test statistic, and then we need to calculate out a p-value. Then it says, do we have evidence? This is a very long statement, or a very long question. So it's going to take us some writing off to the side here. There's no way I can do all this on the electronic screen. Let me discard this, and let's go back to my favorite. Let's go back to here. All right. So let's copy down the stuff that we currently know. So first of all, we know that P over organic, P hat of organic is equal to 275 out of 500 for approximately 0.55. Okay. We also knew that P hat of conventional is 170 out of the same 500, which is approximately 0. Let me check that. Hold on a second. 170 divided by 500, 0.34. We also have to get what's known as the pooled proportion in this problem. I'll call that the pooled p-hat. We need p-hat of organic. We need p-hat of conventional, but we also need the pooled group that it talked about. And the pooled group is easy. We're going to take the 275 that existed in the first group. We're going to add them to the 170 that existed in the second group. And because both groups had 500, we're going to make the group size 1,000. All we're doing in a pooled, all you're doing is add everybody up, including their group sizes, and then get their proportion. Okay, so when I do that, 275 plus 170, and I have 1,000 in my group. Again, I'm going to call this my pooled proportion, is equal to 0.445. We're going to need that number. Okay, so we are testing for difference in proportions, z-value. So we're running this formula right here. Okay, so our first one is 0.55 minus 0.34 minus 0 divided by, it's going to be one great big square root here. We're going to take our, now remember, these are pooled proportion values now. 0.445 times 1 minus 0.445. It's going to seem like we're rewriting a lot of stuff here, but it all matters. Divided by 500 plus, again, pooled proportion, 0.445 times 1 minus 0.445, again, divided by the same 500. Okay? Stall the calculator, stall the, the video for a minute. Get your calculator going. Now take a little while to put that in there and make it all happen. And what I get when I do this is I get a z statistic, or a number of 6.681. That's our z number. Okay? And if you remember what that z number is a statistic from 0 if we normally distribute. And this is always 0. We're all the way out at 6.681, and we're looking to test how much area is there or beyond. Okay? How much area is there or beyond? So we're going to have to go to our calculator now because we want a p-value. So this is our test, this is our z number. This is our value, which we were looking to call our test statistic. Test statistic. Now, we need a p-value. Well, remember, in order to get a p-value, we go to our calculator and we use normal CDF. In our normal CDF, I'll bring up my calc. We use our normal CDF function number 2. Our lower number is 6.681. Our upper number is 1E99. We're on a 0 and a 1 always because it's a z statistic. And look at that bad boy. I got, and I'm going to write this down, 6.681, 1E99. And that thing delivered to me 1.19 E negative 11. Got to move that so you can see it, sorry. There we go, get myself a little bit more room there. This thing's crazy small, right? This negative 11 means take this decimal and move it this way 11 times. This thing is so small that we don't even really need to write out the decimal value of what it is. But this is the p-value right here. P-value. Okay, let's go back to our original value and let's see what this thing says. So, what is our test statistic? Well, our test statistic was 6.681. What is our p-value? Our p-value is 1.19 E negative 11, or 10 zeros, 119. point with 10 zeros, 119. What would our conclusion be? Our conclusion would be to reject this thing all day long. Remember, we were on a 5% significance level, and this value of 1.19 e negative 11 is massively smaller than 0.05. And do we have evidence that the proportion of surviving after eating organic is higher? Absolutely yes. Because remember, the test statistic was seeking evidence that P of O was greater than P of C. And the answer is absolutely positively yes. Gonna do the last one. This exercise refers to a study of hormones replacement therapy in 2002, hormone replacement HRT, taking hormones to replace those bodies no longer making after menopause, was commonly prescribed to postmenopausal women. However, in 2002, the results of a large clinical trial were published, causing most doctors to stop prescribing it and most women to stop using it, impacting the health of millions of women around the world. In the experiment, 8,506 women, okay, so there we go, there's first group, were randomized to take HRT, and 8,102, second group, were randomized to take a placebo. Okay, there's our test group right there. Table 1 shows that the observed count for several conditions over the 5 years. Note that the planned duration was 8.5 years, but the study was terminated as soon as HRT was shown to significantly increase at an alpha level of 0.05, so that's a 5% significance level, because at that point it was unethical to continue forcing women to take HRT. All right, so we've got some data here, and so you're going to want to copy down this data because we're going to need this data for sure. Now remember, we're talking about the cancer all here. We're talking about the 502 out of the total group, which was 8506 right up here. And we're also talking about the 458 right here, cancer all, because we're measuring all cancers, against the 8102. So let's switch off to the side and let's start doing some things. What are we doing here? Let's find that question. Given that the statistic p-value, find the given statistic and the p-value. We're doing exactly the same thing. And we're doing p of h, which is HRT, minus p of p, which was the placebo group. Okay, so let's find the test, let's find the p-value, and then we'll talk about does it influence it, doesn't influence it. Okay, because we got to have a z value. We got to have a z and a p-value first. All right, so here we go. So let's write our statistics down. So our first statistic, let's use p of h first. So p of h, it's the HRT. That was 502 out of 8,506. Okay, and then p hat of p, so this is a placebo group, equals 458 out of 8102. Okay, perfect. We're also going to need a pooled. And notice I'm not doing decimals on this one. On this one, I'm going to put all this into a calculator at one time, and I'll show you what mine looks like. I'll give you time to put yours in. But then I'm also going to do a pooled. Sometimes you want to not round your decimals, and I'm afraid that these will round out. I did one of them first, and I got a very extended decimal, so I'm going to not do that. And in my pooled, I'm going to take the 502. I'm going to add it to the 458. And I'm going to divide that by the sum of the 8506 and the 8102. Okay? So we're going to go get that value first. So when we go to do our statistic value, first thing we're going to have is we're going to have a statistic. And remember, our statistic is going to be 502, 8506, because we're looking to see the difference between this group and this group. That's my statistic. And that statistic is going to minus the null. Nothing going on. And again, I'm working from this formula right here, divided by, this is going to look pretty rough. Divided by, I'm going to use all these fractions in here. So the first thing I'm going to do is I'm going to add together this one up here and figure out what this is. 502 plus 458, that's 960. And 8506 plus 8102, that's 16608. Okay. So that fraction, right, is going to be multiplied against 1 minus that fraction. Yeah, I know. It's crazy, right? And all of that's going to be divided by that group. Plus, it's all going to happen again. 960 divided by 16608. But really all it is keystroke work. It isn't mentally draining. You just have to watch that you're typing properly. Now we got to watch here though, because this group changes to 8102. Okay, oops. All right, so I'm going to stall mine because it's going to take me a minute to put all this into the calculator. And I would encourage you to stall yours, and then we'll all come back here in 1 second, okay? Okay, I'm back with you. Here we go. All right, so that was a beast, right? And here goes to take a look at mine. So notice I used the fractions, and yeah, it took me a moment to put all those in there. However, though, I feel that I had a much more accurate answer. Now, how far off would have I been? I'm not quite sure. I'd have to do it with the decimals and actually see what happens. And maybe when we're done with this, I will I'll check that and I'll see. However, though, I think that, primarily speaking right now, I can use 0.69 for my z value right here. Okay, 0.69 in a rounded state, or 0.68. Maybe we'll use 0.687. I don't know. I don't know what it said. It said round to 3 decimals, actually. I said P value to 3, said Z value to 2. Okay, so 0.69 is our answer. So we'll go back here. And actually, I'm going to go back to here so we can work from there. So now we have a Z value of 0.69. And again, remember, on a standard distribution, we're at 0.69. We're not even at 1, right? So we're about here, and we're going to the curve at the right-hand side there. So we need a p-value is what we need. So we need a normal CDF. Our low number is 0.69, and our greatest number is 1E99. And remember, this was a two-tailed test, okay? So this answer is going to get multiplied by 2. So I'm going to get a p-value, do a normal CDF, 2. I've got 0.69 as my low number, 1E99. Boom, I got an answer. And remember, I'm going to hit times 2 because there's a two-tailing on both sides. I was just calculating the right-hand side. So I've got a 0.490. I've got a p-value. Oops. I've got a p-value at 0.49. I think I had 0. I did. Okay. P-value, 0.490. So what does that say? Well, first of all, there's my p-value. Does HRT influence the chance of women getting cancer of any kind using a 5% significance level? Remember, we did not reject H sub O based on a 0.490 p-value, so our indication has to be no. Hope you enjoyed this. And when we come back, we'll have our last session, which is 6.2. Been a pleasure.